Welcome. I'm TH, a certified flight instructor, and I want to personally welcome all of you fellow aviators who are joining this explainer today to take your skills and really your professional careers to the very next level. Today, we're diving into a comprehensive masterclass on a system you look at on literally every single flight but might not be fully leveraging. I'm talking about the exhaust gas temperature, or EGT system. Our goal by the end of this? Complete, undeniable operational mastery over your power plant. All right, let's get right into it.
Now, to understand where we're going, we really have to know where we've been. Take a look at this classic analog EGT gauge. You'll find this in thousands of legacy cockpits. But this technology actually traces its roots all the way back to World War II. It came from experiments designed to help bomber aircrews stretch their fuel from maximum possible range. Most of these legacy aircraft utilize what we call a single-point EGT system. This simply means a single thermocouple temperature sensor is mounted so it intrudes right into the exhaust stream, just outside the exhaust valve. But, it's not placed randomly. The factory meticulously figures out which cylinder is expected to run the hottest, and well, that's exactly where your one and only probe goes.
Here is our masterclass agenda for today. First, the basics of EGT systems. 2, the science of proper fuel mixtures. 3, finding peak power and efficiency. 4, managing multi-cylinder aircraft engines. 5, the lean of peak debate. And finally, connecting EGT to CHT performance. Section 1, the basics of EGT systems. The absolute secret behind that gauge on your panel is the thermocouple. A thermocouple is simply a sensor that generates a remarkably tiny voltage strictly proportional to the temperature right at the probe itself. To give you some real-world perspective here, a typical EGT at cruise runs right around 1500 degrees Fahrenheit. At that intense, blistering heat, the probe is generating a mere 36 millivolts. That's 0.036 volts, practically nothing. What's truly fascinating is how we process that tiny signal. Digital EGT systems physically amplify this minute voltage to give you incredibly precise temperature readouts. But traditional analog instruments, they just read that raw voltage directly. That's exactly why those older gauges often don't have specific calibration numbers on their face. They're just showing you a raw electrical swing. Section 2, science of proper fuel mixtures. Okay, so everything we do with mixture revolves around an exact chemical balance. When you reach up and manipulate that red mixture control, you're directly altering the ratio of fuel to air. Your EGT hits its absolute peak value when that fuel-to-air ratio reaches precisely 0.067. Chemists call this the stoichiometric mixture. Basically, at this exact point, the mass of combustible fuel perfectly matches the amount of oxidizer, or oxygen, inside the cylinder. Practically speaking, this magic 0.067 ratio translates to exactly 1 pound of fuel consumed for every 15 pounds of air. So the crucial takeaway here is grasping the sheer massive volume of air your engine requires to pull this off. Let's look at standard sea level conditions. Air weighs about 0.0763 pounds per cubic foot. That translates to roughly 0.0102 pounds per gallon. Avgas, on the other hand, is pretty heavy. It weighs 6 pounds per gallon. Because of this massive weight difference, for your engine to maintain that perfect stoichiometric mixture, it has to devour an astonishing 8,764 gallons of standard sea level air for every single gallon of fuel it burns. Crazy, right? Let's prove this with some practical pumping physics on an aircraft many of you probably fly, a Cessna 172 SP or a DA-40. These planes use a 360 cubic inch engine displacement, which is about 1.6 gallons of internal volume. When you're cruising at 2,500 RPM, since it's a 4-stroke engine where only half the strokes actually draw air, it inhales 1,950 gallons of air per minute. Ideally, that'd be 19.8 pounds of air per minute. But engines aren't perfect, are they? With a typical volumetric pumping efficiency of about 75%, you're actually pulling 14.8 pounds of air per minute through the engine. To hit our stoichiometric mixture of 1 to 15, you need exactly 0.99 pounds of fuel per minute to match that air. Multiply that by 60 minutes, divide by 6 pounds per gallon, and you get exactly 9.9 gallons per hour. Boom. That is exactly why your pilot's operating handbook lists a 9.9 gallon per hour fuel flow. It's not a guess, it's pure irrefutable math. Section 3, finding peak power and efficiency. This chart brilliantly illustrates our power dynamics. Notice how the exhaust temperature, that's the top arc, peaks and then drops off on either side.
You'll also see that peak EGT actually increases as you increase your overall power output, topping out for most engines right around 1570 degrees Fahrenheit at maximum power. Because of this specific curve, referencing your leaning point directly from your peak temperature has basically become the industry's standard practice. Now, it is absolutely vital to understand exactly why the temperature drops on both sides of that peak. When you're operating on the rich side of peak EGT, there is insufficient air to match the mass of fuel. This leaves excess unburned fuel hanging out in the cylinder. This raw fuel physically absorbs heat and carries it right out the exhaust pipe, resulting in lower EGTs. Conversely, when you're operating on the lean side of peak, there's insufficient fuel to match the air. Less fuel burning simply means less total energy is developed per combustion event. Less energy naturally results in cooler temperatures. So both sides run cooler, but for entirely different physical reasons. Experimental results show us exactly where our maximum power lives. Maximum engine power is developed when the mixture is set to 100 degrees Fahrenheit on the rich side of peak EGT. At this exact temperature, your fuel-to-air ratio is 0.083. But I want you to clearly understand the trade-off here. At this rich setting, you're consuming 26% more fuel per minute than you would at peak EGT. However, for a given RPM and throttle setting, this guarantees your power plant is producing its absolute maximum possible horsepower. Section 4. Managing multi-cylinder aircraft engines. In a single probe system, you are essentially blind to the other cylinders. How those unmonitored cylinders behave depends heavily on your fuel delivery method. For carbureted engines, air and fuel are mixed as they pass through the intake manifold. While the charge might vary a little bit, the mixture across cylinders is generally quite consistent. Fuel-injected engines? Totally different story. Fuel's injected directly into each cylinder port through tiny nozzles. Because of this, the fuel-to-air ratio in each specific cylinder depends entirely on how perfectly matched those individual injector nozzles are. Because of these tiny variances, every single cylinder is going to hit its peak EGT at a slightly different fuel flow. And this right here is exactly why modern glass panels are a real game changer for aviators. On a Garmin G1000 lean engine page, using multi-point probes, you have total, unprecedented visibility. Notice how cylinder number 6 is the hottest and is peaking first. You no longer have to just cross your fingers and guess which cylinder the factory decided was the hottest. The engine is literally showing you in real time. Armed with that kind of visibility, here is the precise operational procedure for managing a multi-cylinder engine. First, slowly adjust the mixture from rich to lean. Second, identify that very first cylinder to reach its peak EGT. Now pay close attention to this next step. You continue leaning until that first cylinder is 100 degrees Fahrenheit lean of its peak. Doing this assures that all the remaining cylinders are running safely on the rich side of peak. It's a highly calculated method to keep the entire engine block within safe operational parameters, all while maximizing your efficiency. Section 5. The lean of peak debate. If you spend any time around the hangar, you're going to hear the old school argument. Running lean of peak means you're going to burn the engine up. But does that actually make scientific sense? We just proved earlier that the engine operates at the exact same cooler temperatures on the lean side as it does on the rich side of peak. So where does this come from? The root cause of this legacy paranoia was the single probe system. Back in the day, pilots simply had zero visibility into those unmonitored cylinders. That made lean operations genuinely risky because you literally didn't know if a hidden cylinder was running dangerously hot right on its peak. Let's unpack the math and put this myth to bed. If you carefully lean the engine so the hottest EGT is 50 degrees Fahrenheit below peak on the lean side, you ensure all cylinders are well below peak temperatures. Just look at the data for a typical 130-knot aircraft. By moving to 50 degrees lean of peak, your fuel-to-air ratio drops to 0.055. That is just 1 pound of fuel for 18 pounds of air. This yields a massive 31% improvement in fuel efficiency over running 100 degrees rich. And the physical cost for that massive gain? A mere 6% reduction in power, which corresponds to about an 8-knot reduction in airspeed. When you apply this math to a real-world airframe, the results are just staggering. Let's take the DA-40 equipped with the IO260 engine. By mastering lean of peak operations, your fuel economy jumps from 14.4 nautical miles per gallon all the way up to 17.4 nautical miles per gallon. That is a concrete 21% increase in absolute range. This right here is why professional fuel management matters. It directly impacts how far you can fly and, frankly, how much cash it costs to get you there. Section 6. Connecting EGT to CHT performance. It is absolutely critical that we don't confuse these two metrics. EGT is a direct, instantaneous product of the residual heat from the combustion process happening inside the cylinder. CHT, however, is the temperature of the physical metal cylinder itself, and that is regulated strictly by the volume of cooling airflow passing over the engine block. Because of this dynamic, the cylinder with the hottest EGT is not necessarily the cylinder with the hottest CHT. Usually, one of the cylinders furthest aft will have the highest CHT, simply due to a lack of sufficient cooling airflow reaching the back of the cowling.
And this brings us to a really serious operational hazard, shock cooling. Because airflow dictates CHT, a combination of low power, meaning low internal EGT heat, and high airspeed can cool those front cylinders far too quickly. Extended descents are particularly dangerous here. You must monitor both your EGT and your CHT aggressively. Understanding this interplay is essential, not just for stretching your aircraft's range, but to protect the physical integrity of the metal, ensuring flight safety and saving you from some massive, massive maintenance bills down the road. We've covered the history, the chemistry, the rigorous math of fuel flow, and the concrete reality of lean of peak operations. The data is clear, the science is irrefutable. So I'm going to leave you with this question to chew on before your next flight. Are you truly mastering your power plant with this level of scientific precision, or are you just flying by the old school rules? Take this knowledge, apply it to your panel, and fly like the professional aviator you are striving to be. Until next time, fly safe.